finally, the all important Goldwinters and ARIMA models. ARIMA is actually a mix of multiple types. It's a lot of models. In fact, the random walk and everything else can also be stated in terms of ARIMA. Moving average models, everything can be stated in terms of an ARIMA structure. Okay, so we will talk about this. Okay, so first Goldwinters. Gold and Winters. Two people. Gold had a linear model. Winters, being winter and cold or whatever, added a seasonality to that. So old Winters model has seasonality also incorporated. There is a old model also separate, which is only a trend model. It doesn't have any seasonality. Linear model. So just a high level picture of what Goldwinters does, the equations, etc. We don't get into those. We don't. I will show the equations also next page, but nothing to really memorize or worry about. But I will just talk about what they are really doing in these things. As understood, and it's pretty much a lot of it is summary of what we have covered. Three components: trend, seasonality, and randomness. So they have three equations which are smoothing equations. Every period, as new data keeps coming in, the smoothing keeps getting updated. So the three components for the trend, for the seasonality, and for the randomness. There is a smoothing component for each one of those, and there are smoothing parameters alpha, beta, gamma. We will see which one is which. Initial values for the trend and the error are obtained using regression or time method that we had covered. So that is now getting incorporated. Multiple things we talked about put together becomes Goldwinters. Initial value for the seasonal component are obtained using the dummy variable approach on detrended data. So you remove the trend component and then use the dummy variable approach for the seasonal component. So that's what the initial value for seasonal is obtained. Once these initial values are obtained, then they are kept on updating as new data keeps coming in using the smoothing parameters, etc. The error equation, of course, gets seasonally adjusted. Seasonal component is removed. So some error equation is there. This is what goes on in the background. So nothing very, very fancy. Has three components. So three smoothing equations. And exponential smoothing is what is incorporated by default in Goldwinters. So exponential smoothing is done. Regression on time for the initial trend values and detrended data use the dummy variable approach to get the initial seasonal values and then keep updating those according to these equations. Three smoothing equations. There is additive seasonality, multiplicative. That seasonality can be incorporated in two different ways. That's what Goldwinters are also doing. Additive seasonality, error plus trend plus seasonality. Multiplicative seasonality, you multiply the seasonality. Error and trend together and then seasonality gets multiplied. So that's what the equations are for the Goldwinters. The smoothing equations for each period to get that is alpha for the error, beta for the trend, and gamma for the seasonality. And the main thing I want you to see is basically the trend equation is the same for additive or multiplicative. That's the same kind we had seen earlier also when we did that regression on time. Trend doesn't change. There is a linear regression that we do. That is done, taken care of. Seasonality is pretty much getting multiplied. Here it's so this is added. This is the additive and multiplicative. For the additive, these are the seasonality things. Seasonality is getting subtracted, seasonality is getting divided in the other component. Same multiplicative additive, that's the main concept. You add or divide, subtract, those are things that are being done. We won't deal with the equations manually anyway, so we don't get into more details. But the main things to remember are three components, three smoothing equations. There are smoothing parameters, alpha, beta, gamma. Alpha for the error, beta for the trend, gamma for the seasonality, and then initial trend values obtained using the regression or time method, initial seasonal values using the dummy variable approach, and then you keep updating them and using exponential smoothing. Currently uses exponential smoothing. So let's do that. Old winters. How do you think old winters is incorporated in R? Right. Now you are getting very lazy, no? SMS, simple moving, not simple moving average, SMS. So like that, old winters also enter this. No, old winters is old winters. You better type it. But that's all you have to write. Old winters on the time series data and done. Let's do that. Okay, so here is now. First, I am doing old winters on the miles time series data, and I am saying beta and gamma are false. Beta was trend, gamma was seasonality. I am saying there is no seasonality, there is only randomness. So use just the moving average. Just use the moving average, and that's what it is going to be doing. Moving average method essentially. And I run old winter. And this is my output. That's what old winters exponential smoothing without trend and without seasonal component. That's what it says that I am running. Smoothing parameters alpha 0.7, beta gamma false. Anyway, I have said there is no coefficient A for the error term. Because that's the only thing that no trend, no seasonality, only the error component. So that's a moving average method where there are only errors that we deal with. Okay. So that is the component, and these are the fitted values for all the months, all the years, various years. The fitted values are given. Fitting is being done with exponential smoothing. That's all. That's the only thing that is being done. What winters? So till up to December 2012. And now I want to see. So this is what the fitted values look. Okay, fit badly, ugly, yeah, like that. Seems to have fitted. Everything is just fitted. So how do I find out what this fitting is? Error, some error. Of course, I am a bit lazy again here. So SSE is already built into the function. So if I just type SSE, it will give me a sum of squared errors. Sum of squared errors will be a large number, no? 204 data points, and the value is in millions already, tens of millions. So every error, squared error, will actually magnify a lot, but who cares? I just want to compare. Or else you will calculate your MAPE and you will have to write the code. It's a one-line code, but that's too much for me. So the sum of squared errors is 7.4 times 10 to the power 15. Fine. Now this was only with trend and seasonality removed, only with randomness. Let me include trend and seasonality also in both winters. Okay? And so my additive trend and seasonality, I can do multiplicative also. Okay? I think default is additive only. If you want to include multiplicative, you type is equal to multiplicative or something like that. So this is okay. So old winters time series, that's all I need to do. To be able to build a time series model on old winters, I type old winters Done. Error. Yeah, that's what I got done. What happened? I have to run again. Not here. Nothing, no problem. Warning only, yeah? So we don't care about warnings. Okay. Error as a abnormal termination in line search. Something went wrong somewhere. Let's run it again. I don't know, sometimes you just have to run it again. No, this time it won't accept. Requirement 4
complete 304 and 305 you select and execute.
is it?
Yeah. Right.
Man, that's a new thing I have learned today.
Did you run the library for us?
What? 303 also? What is it? Just a warning, let's just continue and see what happens. Okay, yeah, it was just a warning, yeah, sure. So now what we have done is voltmeters exponential smoothing with trend and additive seasonal component. It has by default, when I said voltmeters in time series, additive is by default what is taken. Otherwise, I think you have to type voltmeters. This time it will give me if I change something here. I think type or something like that. How do I figure out what to do? Seasonal, I think. Seasonal equal to multiplicative. That's it. Okay. Now let's see again. Never done this before. Let's see what happens. Okay, it's doing something. Oh yeah, changes things also. Voltmeters exponential smoothing with trend and multiplicative seasonal component. So you can just play with that easily and. Let's see. Okay, I've never done this, so now that I've changed it, let's forecast and see if the error is any better or worse. I've done something, some crazy stuff. Okay, error has increased 10 to the power of 16. Well, something went wrong there. I don't know what it's doing here. Something went wrong here. Anyway, let's go back to our additive stuff. Okay. So now it is. I think the first line also, time series also I have to see. Now it is not addressing. What happened? I think it's supposed to reduce it by order. Let's go back here. Oh. Let me just Going on. Repeated this time it changed the coefficient. So I think some data has changed. Load it again. Okay, so this makes sense. Now let's go back. Okay, so we are back in business. Now, we're going to do this. Now it is done. No, this is okay, very good. So we are back in business. So this is with trend and seasonality incorporated. Very nice, sir. It's all pretty nice actually, all the way to the end, it's also mostly. This is where they incorporate the here. Actually, this is tracking pretty nicely here. Okay? Very nice. So let's end with the error. Okay, yeah, I got that error there. And so let's look at these slides. This is so this was without the trend and seasonality, and this was the total error, sum of squared errors. Once we added the trend and seasonality by an order of magnitude, it has come down. Looks pretty decent also. What I will do at the end of this part is actually I will use this voltmeter model, and once I am finished with Ariba also, I will do forecasting for the next 3 years. And then we will check the error on that one. That's the real part. Okay? And after that, finally, I will do a 5-minute case on another thing where a lot of other crazy stuff comes in all at the same time, and the entire end-to-end picture you will get in 5 minutes. So this was with the trended additive seasonality. Alpha, beta, gamma, beta, the trend data is found into the zero. The smoothing parameter, there is no smoothing needed, but equation has error coefficient, the trend coefficient, and 12 seasonality coefficients for 12 months. The seasonality is also incorporated. That's what this thing is. And you can see for January 1997, the fitted value and then the error, trend, and seasonal components for each value, the breakup. Because you decompose, when you decompose, you get the breakup from. The entire thing is right there. These are the fitted values for all months. Right, that's everything. Finally, once we are done with building a model, we must ensure that we check for residuals. Obviously, if the trend and seasonality has all been accounted for, the residuals should be random. And from ACF and PACF, I should be able to see that there is only randomness left. Okay. So, old winter things, residuals, well, looks like there is something still left out. This is, I think, way out in the 15th month or something. 1 year, 1.5 years. Somewhere in between. So I don't, yeah, but the first one is there. So there is still something left. Old winters has not accounted for all of that variation, and there is still something left. So, but it's still about 0.2 or something actually. So not a very high correlation. So we saw that one randomness. There might be 1 or 2 significant thing, but the magnitude will not be too much. I think we can live with that. Well, we can't do anything else with this model unless other functions that can write it. So now I want to do some forecasting. Forecasting package. So residuals, we have done that. ACF and PACF. The residuals. Library forecast. So now I want to do forecast. And how do I do forecast? Forecast dot voltmeters. And how long? I want for 36 time periods. The time period here is month. So 36 months forecast I want to do because I have the data for that. So I did that. And plot dot forecast. And that's my plot for the forecast. 2012 up to this point I had the data, and from here I have done the forecast data. The blue line is the forecasted value. The orange or the brown range is 80% confidence interval. Why 80? 80. Yellow ones are the 95% confidence interval. Yeah, that's accurate. Okay. So 80% and 95% confidence interval. This is the forecasted value. Okay. So it gives the range where it can be. Decent enough forecast. Let's see if that is decent enough. We will calculate the MAPE for that. Because I have actual values for these things. I have the fitted values, predicted values. I will see what's the error. Mean absolute percentage error we will calculate. Okay, by the way, then we had also done with no trend and no forecasting. And no trend and no seasonality. Okay? Yeah, obviously no forecasting. So, if I do the forecast with that, well, no trend, no seasonality, so it will be a straight line. But you see, confidence interval is increasing because I have forecasted some value for the next time period. Obviously, there will be some error, but I am continuing to go with that. The errors are building up. So my confidence is in a way going down. So confidence intervals keep going up. They keep going up. But if there is no trend and no seasonality, that's what the forecast is going to be. Okay. And that is voltmeters for you. And finally, we will start with, there are a variety of models and some of them are called auto-regressive models, AR, auto-regressive models, where the predicted value or the forecasted value depends only on the past values. Past values only, y t minus 1, t minus 2, so it's a function of the past values. An AR model, it is denoted as ARP. P is the number of significant lags. How many lags? We were looking at autocorrelations, no? How many correlations have significant lag and it's not equal to 0? That's what P is. So P of the past, so is the past yesterday's value significant? Okay, yes. Is day before yesterday also significant? 2. Okay, so 2 lags are significant. AR2, that becomes AR2. Like I said, from here on, there is a bit of subjectivity as well because you have to keep the model simple also. You cannot say for sure that this model is the best thing. So you have to keep simple models. Obviously, we know that a lot of past values, values much farther back in history, won't have an impact today. So you can't have too many lags anyway. There are rules of thumb that we will talk about as we go along, and I will give you a website that talks about all those rules of thumb as well. But the equation for an auto-regressive model will be like this. The forecast is beta 0 plus beta 1, yesterday's value plus beta 2 day before yesterday plus like that. That's an auto-regressive model, just a regression. And if I have to look for the regression lags, how many lags are important, should I be looking at ACF or PSCF? PSCF. PSCF is what we built with regression model. No? We built a regression model. The independent contribution of each lag was collected from there. So AR will be taken from there. P. So AR, P lags. Then there are moving average models where we said if the trend etc. is not the main thing, but randomness is much more. If there is randomness, the way you predict is you actually smooth. You take the smoothing moving averages and that's what you do. How many moving averages should I take? Okay, so moving average models are the ones where the prediction is now dependent on the past errors. How much error I made. It's not on the past values, actual values. It's on the past errors I made. And so it's a function of those. And moving average models, how many lags are important? These lags we take now from ACF. The P, AR, auto-regressive P lags are taken from PSCF. That's the way you remember. P from PSCF. So Q from ACF. Okay? So that's the way to simply remember that thing. And you also notice though that we actually did when we were looking at lags, we were doing a difference, etc. So trying to get those differences which were anyway, that's what it is. That's just too complicated. Moving average models, the Q number of lags, how many lags are significant? We take that from the ACF. So this is where ACF and PSCF come into play. How to select the model, how many lags have to come into play. And this equation looks like a linear equation here, but it's a fairly non-linear equation. So we don't even get into the equations at this time. But then there are models that are a mix of both the things. Auto-regressive and moving average, both are there. Obviously, if there is only a regression kind of a thing, to get auto-regressive models. You see, when we were looking at G stock data, it was like we said, one lag is what is significant. That ends up as an auto-regressive one. AR1 model. You can, so Y is equal to beta naught plus beta 1 times the first lag. That's what is able to explain that. Okay, so that's an AR1 model. But the thing is, these are all mixed up. The same thing I can actually also, what can I do? When we differentiate, we found stationary model. No? So it can just be a difference model as well. So I'll talk about difference in just one more thing. But auto-regression, moving average, they can actually work interchangeably. In the sense that, see, I have an auto-regressive model. There was a straight line. I can, it's a simple y is equal to mx plus c kind of a thing. But I can take a lot of small moving average components and I can build the same thing. So, infinite moving averages can also be used as a replacement for one auto-regression. But then we have to have simple models. So, a simple auto-regressive with one lag works. So, the thing is, they are all interconnected. So, the idea for selection of these models is to keep the models as simple as possible. Keep the number of significant lags in your model as few as possible, because those are these number of components. I don't want this equation to be too long. Moreover, I know that a lot, much past older values are not going to be having an effect. So I really should not be having a lot of past lags anyway. So mix of auto-regressive and moving average models are represented as ARMA models, auto-regressive, moving average. Obviously, auto-regressive has a P number of lags, moving average has a Q number of lags, and the equation will be a combination of the auto-regressive part and the moving average part. Moving average for the errors, auto-regressive past values. And finally, there is something called integration. When we did the G time series data, we differenced it once to make it stationary. Now that I have differenced it, if I want to now forecast, I have to integrate it back in some models. I have to go back in. So differentiation goes back into integration. So how many times did I difference the data to make it stationary? That many times I have to integrate it back. Okay, that's the I. It is denoted as ID. And if you don't difference at all, you don't need to difference at all, then this is I0 to make it stationary. And that brings us to Box-Jenkins methodology, which is used to build the next set of models that we will talk about, incorporating the 3 slides that we have just talked about. What difference? So, whatever amount of differencing you have done, you have to just undifference that part as well. But manually we don't build these things, so it will all be incorporated into the modeling. The ARIMA models that we are talking about. Let me just talk about that. That's where it will come into the picture. Okay. So Box-Jenkins methodology is what this methodology does is you first identify a model. We will see, and that will be the highlight of this session basically. You first identify a rough model by looking at ACF, PACF, etc. But ACF and PACF on what? On the difference data. Box-Jenkins methodology is that you first difference the data, and on the difference data, you do ACF and PACF, and then see if there is any trend, because differencing need not ensure that everything becomes stationary. You have differenced it, and after differencing, is there any trend and seasonality left over in that? And that trend, seasonality, etc., you see from ACFs and PACFs and identify the number of lags, how many times you have differenced, and that together puts together your final model. So, and the model has those the equations that we saw for the auto-regressive terms for moving average. We don't get into the mathematics of that, not really needed for what we do. But what we have to ensure is to understand what is left over in the process. First, we difference the data. Difference data, if everything becomes stationary, that's the model that we have. In the difference data, when we look at ACF, PACF, if there are significant lags, that's where we try to see how many of auto-regressive and how many of moving average terms do we add to the model to account for that leftover effect of trend or seasonality, etc. Okay? So we will do it step by step. I will show this whole process step by step with this data, with which data? I think the same data, but then I have another data that I do a case for. And then, so you identify what is left over, the seasonality and all those things, and then incorporate those in the model. Then you run the model, and the equations, whatever the equations are, they will estimate the parameters, the coefficients, like we saw in Goldwinter's. What is the coefficient for A, B, the seasonal factors, etc. All the coefficients, it does that. Let the system take care of all that. Once it is done, what you have to check for is the residuals. Are the residuals random or not? They should be random. All the trend and seasonality should have been accounted for by the models. And that you do by looking at ACF, PACF to see if it's random. I will also show you one statistical test just for you to know that you can run statistical tests also for that thing, but that's for your information. And after that, if you don't want to do it, you don't have to. Visual inspection is good enough for ACF, PACF. Okay? So that's what the Box-Jenkins does. And this whole process is culminates into a ARIMA model. ARIMA stands for Auto-Regressive Integrated Moving Average Models, where the number of auto-regression models, the lags, number of moving average lags, and how many differences we have done, all of that gets incorporated in the equation to finally make the predictions or to fit the model, to build the model. Okay? So ARIMA, P, D, and Q. These are non-seasonal models. There is no seasonality that we talked about there. There are seasonal ARIMA models called SARIMA models. So, seasonal ARIMA models, SARIMA models, and they are denoted as ARIMA PDQ, and then there is a capital PDQ for the seasonal component, and the seasonal period is given as N. Okay, so seasonal period in our miles time series is 12. Okay, so now how many PQ, etc., how many differences, seasonal differences, non-seasonal differences? I'll go step by step with the data that will be crystal clear that time. Okay, so we do all that to build this ARIMA multiple types model. So just to summarize the ARIMA model process. First, consider a general ARIMA model just by looking at ACF, PACF, what will be the initial model, and then keep updating that. Okay, on the different data, and so there is a model identification phase, parameter estimation phase, and finally the residual evaluation phase. Everything looks good. If the residual looks good, start forecasting, and we will do that. So let's do R, and let's do R step by step. Let's see what is best. Let me actually go slide by slide, and then if need be, I'll go to the code. I think I don't want to lose the flow of the thinking. First of all, to identify a model, that is the identification phase. Plot the data. This is the plot of the data. Okay, done. That's step 1. Step 2, plot ACF and PACF. First, understand what might be going on, and we saw that in the beginning. We said, yeah, there is seasonality there. There is some trend because ACF is decaying. How do I now try to understand that? ACF is decaying, PACF is cutting off. So there is trend is something that is there. Obviously, we also see that seasonal component. So trend and seasonality both are there. Okay, so that is just for understanding. I don't know anything else from here. I have just got to understand that both of them are there. So what do I do? Okay. Okay. So yeah, same thing. This is also called a suspension break pattern. So if that is the case, both non-stationarity and seasonality. That's what we just mentioned. That there is seasonality in there as well. Okay. Okay, so now, first I perform, this is just to understand. So, I have the data, I looked at the data. Data suggests there is, obviously it is not stationary. The ACF, PACF are telling me it's not a stationary thing. I also know that there is some seasonality going on. Anyway, let me first try. Starting off, what do? I do a non-seasonal difference. Non-seasonal difference, what does that mean? Difference. This value minus the previous value. Normal difference that we just saw, we did it. Okay, so now in terms of ARIMA model that I will talk about differencing, I have not done any auto-regression, I have not done any moving average, I have only done differencing. Plain simple differencing can in ARIMA terminology can also be represented as ARIMA 010. What is ARIMA? So you just don't, from now on when you go back, you don't say, oh, I learned how to difference. I learned day 2 minus day 1 subtraction. I did ARIMA 010 model. Same thing. Exact same thing. ARIMA 010. There is no R part, there is no Ma part. There is only the I part there. So what? Okay. So this is what we did. Okay. So let's see the ACF and I did the differencing. So that's the first step. Apart from looking at the basic plot and all those things and to understand what's going on, the first step is differencing because it is not stationary. If it is not stationary, you stationarize. I stationarized it. I am looking at ACF and PACF. This one I have to ignore the zero lag, but I do see that there are significant lags at specific periods. Okay, ACF, this is not decaying. Okay, there are specific time periods. There is something. PACF also is showing the same thing. PACF has some more stuff going on here. There is a bit more sort of decay there. Okay, so maybe. So this is where your subjectivity comes in. You try to build multiple types of models, see which one works better. So here I know there is seasonality. So left. So first thing, instead of getting a non-seasonal difference, I will go back to my original data and I will get a seasonal difference. Because when I undifferentiate, if I already differenced it and then I do some seasonal differencing, some of the seasonality effect might be lost. I don't want the seasonality effect to be lost.